tous. Donc, on est là pour la soutenance de Naouel Haggui. Donc, la thèse, c'est un versatile video coding Dataflow Modelisation. Donc, le jury est composé par des rapporteurs Vaader, qui est professeur au département informatique et Mohamed Ali Benayed, qui est professeur à l'ENET comme des SPACS et en ligne. Et puis un examinateur en a Marco Mattarelli qui est à l'EPPL à Lausanne, qui est en ligne. Il y a Wassim Amidouche qui était qui maintenant est à Abu Dhabi. Il y a Fatma Beidi qui est maître assistante à ST. D'accord. Puis il y a l'encadrant Jean-François Maison, directeur de thèse, professeur à l'ISAREN, et co-encadrant, co-directeur Noé Masmoudi, professeur à l'ENIS-PAX. Et puis il y a moi-même, du Dataflow Modelisation, je suis chargé de recherche à l'Université Paris-Saclay, Centre scolaire. Et je crois que je fais le tour. Donc, Naouel, tu as 45 minutes pour présenter tes travaux.
Hi, everyone. First of all, I'd love to thank you all for being here today, and I'd love to thank all the jury members for accepting to be here today. My name is Naouel Haggui, and today I'm going to defend my thesis entitled Versatile Video Coding, VVC, Dataflow Modelisation. Through this presentation, we are going to start with an introduction in which we are going to talk about video coding, Dataflow modelization. We will reveal after that our objective. And after that, we'll have the first contribution, multiple transform selection, MTS, EBSDF model. After that, we will have the second one, which is MTS, ESDF model. Finally, we will delve to the last contribution, that is a full Dataflow model for a full decoder. And finally, of course, some perspective and conclusion. Let's start it. The video consumption has shown a significant increase, especially in recent years. This could be, according to Cisco, video has reached 82% of global internet traffic in 2022. This phenomena could be explained by various reasons, such as the appearance of new video format, the appearance of a variety of devices, and also the huge use of video websites, such as YouTube, Netflix, the huge use of gaming platform, and the huge use of video conferencing, especially since the appearance of COVID-19 that forced us to stay at home and unfortunately remote working. In order to be able to watch this video, transfer them, we need to solve some issues. There are two of them that are, we need to compress the data, and we also need an optimized implementation. So let's start with the first problem, that is the need to compress data. To solve this issue, we need to process a process called video compression or video coding, with aim at minimizing the video size while maintaining its quality. This process has been standardized, and a variety of standards has been appeared through years, such as AVC that target HD resolution, HEVC that target full HD resolution, and the latest one, versatile video coding VVC that could target 8K resolution. And this is the one that we are going to work with. Compared to HEVC, VVC enables 14 to 50% of coding gain for the same visual quality. This is the structure of the VVC standard. It has a hybrid structure similar to the HEVC standard. The process starts with partitioning a frame into different parts. After that, these blocks will be transferred to the prediction unit, in which we will have either intra or inter prediction based on the content of these blocks. Then those results will be sent to the transform unit, next the quantization unit, and the resulted coefficient will be sent to the encoding, the entropy coding unit, in which this coefficient will be transformed into binary syntax that could be stocked and then decoded by the decoder. As you can see here, there are many units. So there are many data dependencies that are complicated and difficult to optimize. It is true that PVC has enabled a lot of advantages, such as support for new video format. It is easily configurable for various application needs. However, it has some drawbacks. It increased the complexity of both sides, the encoder and the decoder, so that there is a higher energy consumption, thus higher impact of a higher carbon impact in our environment. Now, to solve this, the research has been carried out, some of them by the use of machine learning and others by exploring parallelism between tasks that could be processed independently at the same time. This research will focus on the second solution, that is exploring parallelism between tasks. Actually, since the appearance of Moore's law, the industry have moved toward the creation of multi-core architecture as modern application exceeds the capability of single-core architecture. So that, however, the creation of such a multi-core algorithm in order to be implemented there is not an easy task, so that we need to design a design methodology that facilitate this task. We need the design methodology that help us to create the multi-core algorithm. One such methodology that has proven to be effective, especially in signal processing application, is Dataflow modeling, which is the solution also for the second problem, which will give us an optimized implementation. So what is this Dataflow modeling? Well, it's a network of computing units exchanging information through unidirectional buffered links called PFOs. As you could see in this figure, there are two actors that are linked with a FIFO in order to communicate. Why we choose Dataflow? Well, because it's useful for capturing important data dependency. It is useful to explore parallelism between tasks, and there is another important reason. Actually, if we compare Dataflow to other approaches that used to create the multi-core algorithm, for example, OpenMP, OpenCL, Bthread, etc. For example, if we need to create a multi-core algorithm for an X architecture, we need months and months of development. And could we use this multi-core another architecture? For example, a Y architecture? No, we need to create a new one. So that a new months and months of development. And the circle will keep going round and round. However, what happens when we use Dataflow modeling? We have an X architecture. We create our Dataflow model. Do we need to create another one for the Y architecture? The answer is no, because we already have one. So the same model we could apply on different architecture, such as FPGA, x86, etc. So, which makes Dataflow goes for the win when why comparing it to other approaches used to create the multi-core algorithm. There are a lot of variety of existing Dataflow models. The one that has first appeared and the one that is considered the mother of all is called KPN. After KPN, there has been appearance of other extension. Each time a searcher adds a feature, they add analyzability, but the expressivity is getting lower. If we see here this picture, we could see that if we are going from the downside to the upside, the expressivity is getting higher while the analyzability is getting low. And vice versa, if we are going from the upside to the downside, we could see that the analyzability is getting better while the expressivity is getting lower. Here in this table, we show different kinds of Dataflow model with different features, such as expressivity, decidability, reconfigurability, etc. As you can see here, they have also different expressivity. In order to create a Dataflow model for a complex application, such as video coding that contains a lot of data dependency, we need to use a Dataflow model or kind that is characterized with a high expressivity. For example, the DPN over here shows a tuning expressivity. However, this DPN has been used in the past to create other data flow models, such as, for example, this one that is an RVC call model for HEVC standard. This model has shown 15% less efficient than HM 9.0, and it was 5 times less efficient than OpenHEVC. Another study has showed that a full decoder, full data flow model for a full decoder based on the Y UV parallelism. So here, this result shows that the model has shown a lower FPS compared to the reference decoder. And OpenHEVC has outperformed both the reference model and the proposed model. So, which poses a question here, which gives us that it is true that using a data flow model that has a Turing expressivity can be used to create the model. However, the performance wasn't that good. So we have going to some research, and we proposed this question. Is it possible to use data flow models that are less efficient, less expressive than the DPN, but it have a more analyzability, and we could achieve a good result or not? So is it possible for you to model the application first, and it is possible to have a good result also? This is the thing that we are going to discover during this thesis. As in every application or project, we need to employ some tools to help us achieve our goals. The tool that has been used in this thesis is called RISP, which is a rapid prototype, an open source rapid prototyping tool that helps the automatic generation of multi-core algorithm. In order to create the model, we need to perform different inputs, such as algorithm graphs that shows different actors that are linked with people, which describe the process that we are going to model. We have the architecture graph that shows different cores of the system that we are going to use, linked to a shared memory. After that, we have a scenario and a workflow. This scenario is a very, very, very important item, as it contains all the parameters that control the application performance, such as the algorithm path, the architecture graph path, and the most important thing, the execution time of the different actor. Actually, the scheduler thinks by default that the actor has execution time equal to 100 time units. This inaccurate knowledge of actor execution time could result in a bad decision by the scheduler, so that a bad result, and we don't need that, we don't want that. So that each time we made a modification on our algorithm graph, we remeasure the execution time of each actor and update our scenario with the new values. The last item is the workflow that contains all the tasks that the prism could perform, such as the task that could generate the metaphor algorithm, the task that display the Gantt chart, and we have also some optimization tasks, such as software pipelining and memory optimization. This thesis also will be formed an opportunity to testify the efficiency of the different tasks, as in the past, they have been only tested on a less complex application. So it's an opportunity to testify their efficiency now. I know that I have talked so much, so let's resume our goals. So as a first, we want to see if it is possible to create the data flow model with use of ESDF and eBSDF that characterized with less expressivity than the DPN, for example. And we want to see if we are going to have a good performance or not. And finally, of course, we aim to identify a new requirement for the PRISM tool, for example. So let's begin. So the question from where we are going to start, because the coding process characterized with different units, they are linked, etc. So we have that question, from where to start. There are two strategies to be used in this case: a top-down situation or a bottom-up situation, which means for the bottom-up, we are going to start with a small thing that it is contained of the coding chain. There we are going deeper. However, the top-down, we are going from a bigger thing, a complex application, and we are going in the inside. However, as in our lab, previous work has used a small part of the coding chain called the multiple transform selection, and have implemented this on an FPGA implementation, and shows an efficient result, so that we decided to go with a bottom-up situation. So we are going to first start with the MTS concept to be modeled and study if it is possible and efficient or not. So let's start with the MTS, and with the first contribution, that is multiple transform selection, EPSDF, Dataflow model. So this is the coding chain. We have here a unit called the transform unit. This unit is composed mainly from two parts that are the multiple transform selection, MTS, and LFNST. Here we are going to focus on the MTS. The MTS has been introduced first in PVC, and it enables the decoder to choose the transform that minimizes the rate distortion cost among predefined trigonometric transformation, including DCT2, DCT8, and DST7. The principle is quite simple. If we have chosen DCT2 for the first side over here, we are going to use DCT2 on the second side also. However, if we use DCT8, we have to use two things, either DCT8 again or DST7. If we choose DST7 for the first direction, we can apply both DST7 or DCT8, which make 5 possible transformations that could be done. So this MTS concept characterized with 3 main features that are: first, the butterfly decomposition for DCT2, which enable the deducing of a larger block size from smaller one. The second one is the zeroing out, which means that actually, in order to reduce the complexity of the transform unit, high frequency coefficients are zeroed out for larger block size. By larger block size, we mean the blocks of sizes 64 for DCT2 and sizes 32 for DST7 and DCT8. Last feature is that DCT8 can be deduced from DST7 and vice versa based on this equation over here. So after knowing this information about MTS, we were able to create 2 data flow models with different granularity, one with a fine-grained granularity and the other with a coarse-grained granularity. I know that you are asking the question, what is this granularity thing? Well, we will explain that while tackling the model one by one. And let's start with the fine-grained granularity model. As you could see here in this model, this actor called MTS concept has a different color than this one. That because this actor is a hierarchical actor, which means that inside it, there are different other actors. As it's here, there are several. So those for the DCT2, for the DCT8, etc. They are all structured in the inside. So that the MTS concept here is divided into several actors, and each actor will perform a small instruction or which make this fine-grained granularity model. This fine-grained granularity model has resulted on an execution time on a single core lower than on 2, 3, and 4 core. Shocking, right? Normally, while applying parallelism, while increasing the number of core, the execution time should be decreased, not the opposite. And our result shows the opposite for of the theoretical case. The theoretical case shows is the curve on red over here shows just the opposite of our experimental result. So there are different reasons that explain this fact. Is that in this kind of model, all the process that the operating system performed, such as create thread, make them communicate, synchronize them, provide time, memory, and peripheral management tool, are considered. The synchronization in this kind of models turns to be very, very costly. So, in a nutshell, to achieve efficient performance, task management and data transfer time should not be too long with respect to the computing time of the actors. In this fine-grained granularity model could result in a better result while using x86 architecture if we send different blocks to be transformed at the same time. If we see over here, while increasing the number of blocks, we are getting closer and closer to the theoretical case, the green curve over here. So it is true that fine-grained granularity wasn't performant in x86 architecture, but it could be efficient while using other architectures such as PGA. But since we are going to work with x86 architecture, we decided to explore another type of parallelism, which is to process different blocks at the same time and create a coarse-grained granularity model, which mean that the actor over here, as you can see, have a similar color than this, like this actor, and which make them a coarse-grained granularity. There is nothing inside this actor. The result was better. We were able to realize a speed up equal to 1.8 while using a 2-core x86 architecture. And we also have another result while using a 4-core x86 architecture, and we have a speed equal to 3.8, which is too close to the theoretical case that is equal to 4, which proves the efficiency of the proposed model. Here we shows other result on a 4-core x86 architecture that also shows that our experimental result presented in the red is too close to the theoretical case presented in the blue curves. Also, this was realized into a 24-core architecture, and we were able also to have a good performance, which also proves the efficiency of our proposed model. Here are other important results that shows a comparison between our model and the OpenMP approaches. As you can see here, the OpenMP is presented in the purple color. However, our result is presented in red color, and the theoretical one is in blue. We could see here that our model is more performant than OpenMP, and our model is too close to the theoretical case, which proves that with the use of Dataflow model, we could achieve a better result with a less development time. So, it is now, as we are going to use a bottom-up situation, we have started with the MTS concept. We need to implement it in a real encoder or a decoder. However, this is not going to be happening directly, so that we will have a second step before doing that, which lead us to the second contribution, multiple transform selection, MTS EESDF model. As you could see here, a picture could be divided into a variety of number of blocks. And those blocks are with different size, so that the transform order and the block size are different in our graph. However, the coarse-grained model presented previously, the block size and the transform order cannot be changed at runtime. If we are going to send a transform order to equal to 4, it's always going to be 4. So this could not be changed at runtime. However, there are different possible combinations from block size and the transform order. So if we need to implement this in a real encoder or a decoder, we need an executable for each combination between these two parameters. For each combination between the block size and the transform order, we need to create an executable. And we also need an executable that will compensate all of those, which make us need 26 executable in total. However, and which could be done, but it's not that easy to do. And it's not really that we have another solution that could be better. So that we decided to create a new model which enable the change of these plot parameters, the block size and the transform order at the runtime. And in order to realize that, we have used an extra tool called Spider, which enable the change of parameters during runtimes. We have, compared to the PSDF model, the PSDF model contains an extra actor called parameter control that will enable the dynamic behavior of application. So for example, if we have a transform order equal to 4, it could be changed after that to 8, 16, 64, etc. This actor is made in a way that will enable all the possible combination between the block size and the transform order. So the result, now it's time to testify the efficiency of the model. And we have here for some combination, 4x4, 4x8, 6x4 blocks, 4x32, etc. For all of those sizes, we were able to have a good result, and all of them, for all of the block sizes, we are too close to the theoretical case. Here are the results for the other sizes of the blocks on x86 architecture with 4 core, and here with a 24 core. We also could see that for the all block size, we have speed up that is too close to the theoretical case presented in the blue curves, which proves also the efficiency of our model. As we, in the first contribution, we say that granularity wasn't performant because the data transfer time was really huge. So that with the use of Spider, it could help us to measure the overhead of the application and the execution time of the application. So that with the use of Spider, we have measured the overhead of the application and the execution time for this EPSDF model. And we could see here that overhead time is too low with comparison to the execution time. It's even could be neglectable. Here we result on 24 core, and we have the same result. The Spider overhead time is too low compared to the execution time, which shows that while using the coarse-grained granularity, we don't have this overhead time that could be happened by using granularity, and proves also the efficiency of our model. Normally, here with the next step, after we have an efficient model, is to implement it directly on a decoder or an encoder. However, we didn't have a full decoder that is already done. So, and we, as we are needed to a coarse-grained granularity model to have an efficient solution while using x86 architecture, we decided to directly move to the top-down situation and create a data flow model for a full decoder, which lead us to the last contribution, OpenVVC decoder Dataflow model. Before talking about the Dataflow model, let's talk about the VVC decoder itself. This decoder has different blocks. It starts with the entropy decoding process that is based on Quebec and will be responsible on transforming the binary syntax into syntax element that will feed all other parts of the encoder. It will be here, there, and there. After that, we have the block reconstruction parts in which, of course, we are going to reconstruct the model. This block reconstruction is formed by different units that are the transform, inverse transformation, the quantization, the intra-prediction, and the inter-prediction part. After that, we have the in-loop filter that is formed by DPF, SAO, and ALF. This will be responsible on removing the artifact from the reconstructed pictures. But the question here, where we could top up parallelism, which part that could be used to create the parallelism, which lead us to talk about parallelism strategy that exists in VVC standard. There are three possible parallelism strategy. The first one is the data level parallelism, which is based on SAMD instruction, which means that it is usually applied for process that use the same process applied on different data points, such as especially process that uses vectors and matrix. The transform actor, well, the transform unit will be a perfect target for such optimization. We have also the frame level parallelism, in which obviously the frame that they can be processed independently at the same time in parallel. And finally, the one that interests us the most is tile level parallelism. Tile are rectangular region of the frame. This part could be that contains entire CTUs. Does this part could be processed independently at the same time? The answer is yes. How so? Well, because the prediction dependency across tile boundary are broken, and the entropy coding is initialized for each tile, which makes parallelism between tiles perfectly possible. So here we were able to, and we have a small little investigation to perform, which is to find the different decoder compliant with the VVC standard. We have three over here that are the VTM, that is the original one. We have the VVDEC and the Open VVC. The question is which one is characterized with a high performance? The answer is Open VVC. It is a software decoder compliant with the final version of the VVC standard. It is based on C programming language, and it is integrated as a dynamic library with FFmpeg player. And this this decoder could take advantages of the three level of parallelism that we already talked about: the data level, the frame level, and the tile level parallelism. So that we choose the OpenVVC to use as a reference to create our Dataflow model, and we were able to create. So in order to create our model, we are going to have different steps. The first step is to implement the OpenVVC project as an external library in our project. After that, we will have to disable the use of all function that enables the thread that uses the thread for the frame level parallelism and the tile level parallelism. And finally, of course, we will create the Dataflow model, which leads us to talk about the model. As you can see here, there are different actors that are different units. The first actor on the left here, called attach stream, is responsible on attaching the bit stream to the decoder and starting the decoding process. After that, we have frame information extraction, will obviously be responsible in extracting the different information about the frame, especially the null unit, that will be after that sent to the frame decoding actor via a variable called PU, which contains a vector of null units. After that, the frame decoding actor obviously will be responsible on decoding of the frame. After that, we have the frame receiving actor that will pull the decoder to see if the next image in the decoding process is ready or not. And finally, of course, the data stream that will be responsible on ending the process and the reinitialize the. As I mentioned before, here we are more interested in tile level parallelism. So that, if you notice, the frame decoding actor, it has a different color over here, which means that it is an hierarchical actor, and inside there are other actors. So here we have the slice, the three main actors that are the slice selection, responsible on selecting the slice, tile decoding, responsible on decoding tiles, and non-tile decoding actor that will be responsible on decoding null unit that doesn't have information about tiles. As we, in order to achieve the parallelism between tiles, we have used an actor here called tile number that will be responsible on decoding this actor, duplicating this actor in different dash. For example, if we have tile number equal to n, the tile decoding actor will be duplicated n times, and those n times will be processed independently at the same time. And here comes the parallelism of the tiles. Of course, we need, in order to testify the efficiency of the model, we need to create bitstream that contains entire stack. So that we used full HD and ultra HD resolution sequences, as those are the sequences that contains that has the highest resolution. And with the rise of the computing complexity of the BBC sponsor, there is a critical issue, especially for high frequency, high resolution sequences. Another reason is that with high resolution comes high granularity of actor, which is an important factor in order to have a good result while using x86 architecture. I was able to create 3 tile configuration, 4x3 configuration for horizontal split by 3 vertical split. We have 6x2 and 6x4. So we made 3 tile configuration. Now it's time to testify the efficiency of the model. We have here, in order to have a fair comparison between our decoder and the OpenBBC decoder original one, frame level parallelism has been disabled, and this comparison will be made only on tile level parallel. We could see here that our model and the OpenBBC model that were assessed in different value of QP, 22, 27, 32, and 37. For all of them, our result and the OpenBBC result for Ultra HD resolution, while using 12, 4, and 12 tiles, well, the result were too the result were too close, which makes our model efficient. We have also here on while using full HD resolution sequences, and we have also a good result here while using 24 while x86 architecture, and we could see also that our decoder is slightly above that of the OpenBBC decoder. So here are some other results while using ARM architecture with 6 core, and we were able to achieve a good result also. Our decoder and the OpenBBC decoder are too close to each other, which make model effective. As we have seen here, so the execution time, for example, the speed up over here while using 24 core machine for our model is equal to 11 while using 24 core machine. However, while you normally, theoretically, we will have to, while using 24 cores, some of you may think that we have to obtain a speed up equal to 24, and having 11 is not that bigger. However, That's not true, because the decoding process is basically sequential. It's not 100% parallelizable, which makes the result perfectly logical. So another reason that explain the discrepancy between the theoretical case and the experimental result is the fact that tiles doesn't have the same sizes. For example, if we see this tile over here, we could see that this one contains 3 CPUs horizontally. However, this one contains only 2. There are different sizes. And we also know that in a frame, the details differs from one pixel to another, so that from one CPU to another, so that from one tile to another, which make the decoding time of tiles different. We could see here the decoding time for each tile, and we could see here for tile number 1, for example, the execution time is lower than this one presented in the tile number 21, for example. And this also explains the discrepancy between those results. So, another important result to share is the result spending by our Dataflow model while using single core architecture. As in the previous Dataflow model for full decoder, they have shown a good result while using multi-core algorithm. However, while using a one single core architecture, the results are going lower and lower. However, for our model, if we compare it to OpenVBC, the original one, and the VTM 12.0, the original one, we could see that we could have a good result for while using a single core architecture. For VTM 12.0, as an average, we could see 32.1 seconds as a decoding time. For OpenVBC, we have 11.11, and our Dataflow model is 10.25. Which also means that our model performs well on multi-core algorithm and also on a single core architecture, which proves also the efficiency of the model. So let's conclude. As first, we have started with different objectives. Our first objective was to show if it is possible to create Dataflow model with low and medium expressivity Dataflow models such as EBSDF and BESDF model. And we were able to create several Dataflow models, such the models for the MTS and for the full decoder, so that it is possible to create the models with the use of SDF and EBSDF, which means our first goal has been achieved. The second goal was to see if it is efficient or not, the model presented. And we, for all the Dataflow model that we have presented, we have shown a good result on x86 architecture. And we have shown the efficiency, that fine-grained granularity is important for that the granularity is really important to a factor that impacts the application performance. Fine-grained granularity could be good for FPGA, but not for x86 architecture. And so that our second objective has been also achieved. And the final one is to identification of a new requirement, which are going to lead us to talk about the perspectives. As a first perspective, we aim to apply a new clustering methodology. For example, if we have a fine-grained granularity model, we could transform that in a coarse-grained granularity model in order to adapt the target architecture that we are going to use. For example, if we have fine-grained granularity model and we are going to apply it on x86 architecture, we transform that by clustering to become a coarse-grained model. We also aim to use FPGA or GPU co-processing, as for the moment it's not possible to do that, but in the future we are aiming to support this for the present tool. And finally, we aim to use heterogeneous architecture exploration. We are going to discover which architecture we have to use, that are the different number of processors that have used, etc. So this was my presentation. Thank you very much for your attention, and please be free to ask your questions.
Merci Naouel. Donc là, je laisse la parole à Poita pour commencer. On va démarrer avec Mohamed Ali Benayed.